the third day of advanced training program of PRISAL Foundation, and this training program, which explores pharmacy professionals, researchers, students in the practical hands on novel drug delivery system. And this novel drug delivery approaches definitely will give you practical based activity, which is the first step for our pharma profession and moving towards the entrepreneurship skill development. With this way, today's we have our resource person, and I would like to welcome Dr. Bapi GORAIN, who is the senior lecturer, School of Pharmacy, Faculty of Health and Medical Science, Taylor's University, Malaysia. I would like to welcome Dr. K. Anand, Research Scientist, Department of Cattle Pathology, School of Pathology, University of Free State, Bloemfontein, Campus, Free State, South Africa. Now I would like to invite our first resource person, Dr. Bapi GORAIN, and I would like to brief about his profile. Dr. Bapi GORAIN, he is working with Lincoln University as a deputy dean, and he acquired internal and external research grants for various funding bodies. He has obtained his doctorate in 2002 and master's in 2004. Shall I repeat? His bachelor degree in 2002 and the master's in 2004 and doctorate in 14 from Jadavpur University, Kolkata, India. Dr. Bapi experience emphasis on nanocarrier-based formulation development in circumventing issues with poor solubility and biological barriers to improve bioavailability of therapeutics. He has contributed to various books, chapters for international publishers and articles in the prestigious international journals. And today he is going to deliberate his talk on nose to brain delivery of nanotherapeutics, a boon to target CNS disorder. Welcome you once again, Dr. Bapi.
Thank you so much. Thank you for your nice and warm introduction. And first of all, I would like to thank you for organizing such an interesting event for the pharmacy personals, researchers. And I would like to extend my gratitude to the organizing committee, especially to you, Dr. PRITI, Professor PRITI, for inviting me for this talk. So thank you.
Thank you, Doctor.
So, although this is morning to you, I should wish you a good morning, but it is no more morning in Malaysia. So it is already 1 o'clock, 10 past 1. So good morning to the participants. Let me share my screen first. So, is my screen visible to you?
Yes, sir.
Okay, thank you so much.
Voice.
Voice, is it clear?
Okay, now.
Okay. So the topic which I'm going to talk this morning is nose to brain delivery of nanoemulsion, a boon to target CNS disorder. So in order to cover the topics, I'll discuss on CNS disorders and blood-brain barrier, different limitations associated with the conventional therapy. As we are focusing on nose to brain delivery, the concept and the transportation mechanism will also be focused in this lecture. We will discuss on contributing factors for nose to brain delivery for the delivery of nanoemulsion. Next, we will focus on different strategies to modify the nanoemulsion when we are delivering through intranasal route. And the existing challenges will also be discussed in this lecture. So when we are talking about CNS disorders, it includes the diseases related to central nervous system and brain. So it could include from meningitis, encephalitis, stroke, brain, or other CNS cancer, traumatic brain injury, spinal cord injury, Alzheimer's disease, Parkinson's disease, multiple sclerosis, epilepsy, migraine to headache. Everything will be covered under this CNS disorders. So a recent
intentional. So when we are talking about intentional, it's very difficult to handle this kind of scenario because it's all about the intention of doing things.
I'm sorry. What I was talking about, a recent study has been published in the Lancet Neurology, where diseases, injuries, and 1990 to 2016, they have studied in 195 countries in order to establish the list of diseases. So in that, they have considered 264 diseases in which they have concluded that this CNS disorders are causing deaths after the cardiovascular diseases. So further, this CNS disorders are also increasing day by day because of the increasing number of older peoples around the world. According to the National Institutes of Health, they have gave the estimates that in 2015, around 8.5% of world population were aged above 65 years. However, they have estimated that in 2050, this number will become, this percentage will become doubled, 17%. So we can assume that whenever there is an increase in older people, the chances of getting CNS disorders, let's say the Alzheimer's disease or Parkinson's disease, will also increase. So whatever the available therapeutics are available for these CNS disorders are mostly through oral or parenteral routes. If we take the examples of Alzheimer's disease, we are having 5 different approved drugs for the treatment of Alzheimer's disease. Those therapeutics are available for oral dosage form. So whenever we are exposing our system with such doses, what happens? It will get dissolved into the gastrointestinal tract. Thereby, it will be absorbed by the portal veins. It will reach to the liver, from where it will come to the circulation. So the drugs are reaching to the circulation first, from where it will be distributed all over the body. From the blood-brain barrier, it is crossing the blood-brain barrier to reach to the central nervous system to prevent the disease condition. But in case of Alzheimer's disease, it has been shown that it's creating huge side effects when we are administering the drugs to the elderlies. So this routes of administration creates a problem to the persons. Why? Because to cross the blood-brain barrier, it's a big challenge for the conventional routes when we are administering. So why this blood-brain barrier prevents such drugs to avail or to reach to the brain? Because this blood-brain barrier creates the tight junctions, the special barrier to prevent the brain, the central part of the body, which regulates all other activities uh, from the external stimuli, external components. So this is the normal mechanism by which this blood-brain barrier prevents exposure of external stimuli or chemicals to the brain. So if we see the history of this on concept of blood-brain barrier, we will find earlier to 1987, the theories includes only the tight junctions. So the tight junctions prevents the transportation of the drug from the blood capillary to the brain. But later, after 1987, the concept was changed and presence of parasites, because of which the drugs can easily cross the gaps and can reach to the interstitial fluid. But in case of brain, this is not possible. Apart from which, these endothelial cells are partly covered by parasites and fully covered, the endothelial cells and the parasites are fully covered by the astrocytes. So if we closely see in another aspect, we will find this is the presence of tight junctions, and this is the astrocyte, and this is the parasites. So these tight junctions are created by the claudins, occludins, and junction adhesion molecules. And if we closely observe the mechanism by which the transportation of the drugs from the blood is prevented to reach to the brain, we'll find that presence of different vesicles within the cell. So that is the first criteria which prevents the transcellular transportation of the drugs to the brain. Transcellular means through the cells. So whenever a drug is crossing the cell, if there is a vesicle present, that will prevent further transportation of the drug to the other side of the cell. So this vesicles prevents the transportation further. The paracellular transportation, which occurs in between the cells, is prevented by the tight junctions. So which is prevented by the tight junctions. So both the transportation, the paracellular and the transcellular, are prevented by the blood-brain barrier, the structure of the blood-brain barrier. So whatever the routes of administration we are administering, we have to cross the blood-brain barrier, the conventional routes. So if we administer these drugs, if we wanted to deliver the drugs to the central nervous system, we're having two techniques. First one is the invasive techniques, by which we are delivering the drugs to the central nervous system, which includes the osmotic pumps or depot formulation, from which the drugs will be delivered directly into the cerebrospinal fluid, from where it will reach to the brain. But results have shown that if we are using such techniques, it can lead to inflammatory reactions or damage of the neurons, which limits the use of such invasive techniques. Further, these invasive techniques includes the disruption of blood-brain barrier. So this disruption definitely will not be permanent, temporary disruption. How? We can use the concentrated solutions of mannitol. We can use the concentrated solution of urea or arabinose. So if we introduce the concentrated solutions, hypermolar solutions, into the carotid artery, the blood will carry it out to the capillaries to the central nervous system. So when a hypermolar solution is transported, what would be the tendency of the solution? It will try to become the isoosmotic with the blood plasma. So when if in the process, it will absorb the fluids from the cells. So when it will absorb the fluids from the cells, it will cause shrinkage of the cells. At the same time, the fluid will become isoosmotic. So this shrinkage of the cells, the epithelial cells of the blood vessels, will allow penetration of the drugs to the brain. So this is one concept by which we can increase the penetrability of the drugs. Further, few of the therapeutics are also available, which helps in the penetration of the drugs through the blood-brain barrier, which includes the histamine or vasoactive peptides. So they increase the penetration or penetrability of the drugs by inflammatory reactions. Further, we're having focused ultrasound. This is the novel technique by which we can increase the permeability of the brain capillaries at a particular region of the brain. So the intensity of the ultrasound will be low, and similar to the other two categories, this will also not permanently damage the blood-brain barrier. So it will, the effectivity of this ultrasound may last from 4 hours to 24 hours. This will increase the penetrability of the drugs through which the drug can permeate to the brain. So the activities of anti-amyloid beta antibodies against amyloid beta plaques in Alzheimer's disease has shown promising effect by using this focused ultrasound. At the same time, doxorubicin has also been tested in glioblastoma. So these activities have shown promising results when we are using this focused ultrasound. However, these are invasive techniques. Other technique includes the non-invasive techniques. We all know that the partition coefficient helps in the penetration or permeation of the drugs to the brain. If we are having the log P value higher than 2 or 3, it will help to the penetration of the drug to the brain. So in that case, we can change the solubility of the drug in order to improve the penetrability of the drug to the central nervous system. We can improve the solubility by means of prodrug concept. Further, we can improve the penetrability by viral vector approach. So, and we can inhibit the efflux transporters. So, what is this efflux transporter? If we call about the P-glycoprotein, P-glycoproteins are present in various types of cells in our body, including our gut cells. So whenever we are administering the therapeutics, even though they are having the lipid solubility, it will enter into the cell. But because of the presence of this efflux transporter, it happens to the drugs when we are touching our system. So if the drug is PGP substrate, P-glycoprotein substrate, then it will be effluxed back to the blood capillaries again. So it will not allow the drug to transport to the brain. So if we administer any efflux transporter inhibitor, that can inhibit the efflux transporter, which will help the penetration or permeation of the drug to the brain. Last but not the least is the nanocarrier approach. We are aware that nanocarriers are increasing the approach of nanocarriers to improve the delivery, to improve the efficacy of the drugs has been increased tremendously in recent research. But if we are targeting the brain, and if we are administering through conventional routes of administration, let's say oral or parenteral, then it will also expose the systemic circulation or the other healthier cells with the therapeutics. Novel routes has also been exposed in the research, that is intranasal route. If we see through this intranasal route, we can apply the formulation to this intranasal region, from where you can see the roots like appendages. So these are not roots actually, these are the nerve terminals of the trigeminal nerves and the olfactory nerves. So the drugs can be permeated through these nerve terminals to the brain directly, circumventing the blood-brain barrier. So we need not to expose the systemic circulation by the high load of the drug. If we see this nose to brain research, which are published during 2016 to February 2019. So we have analyzed this data, and we have published in our previous article in International Journal of Pharmaceutics. So where we have shown that 131 articles has been published during this period, which has targeted nose to brain delivery of the therapeutics. So they have used different formulation aspects in order to deliver the drugs, which includes the lipid nanoparticles, around 18.32% of the articles under this lipid nanoparticles. Polymeric micelles were 4.58%, nanoliposomes were 9.92, and polymeric nanoparticles were around 32%, in which titration nanoparticles were 14.5% and polymeric nanoparticles were 17.56%. So among this, we find that the micro and nano emulsions, they contribute around 27.48%. So this can show that the increasing interest of the researchers towards this nano emulsion. Now we will move to the where we will be applying the drugs, and this is the olfactory bulb through which the transportation will occur to the brain. So this is the olfactory bulb, and this is the nasal cavity where we will apply the therapeutic by means of any formulation. So when we apply this, what generally happens? It results in transportation of the drug to the brain via this olfactory bulb. If we closely see what happens here, we will find that the presence of the nerve terminals at the application area helps in the transportation of the drug therapeutics to that nasal mucosa. So when we are applying this, that causes transportation of the drugs through this nerve terminals to the olfactory bulb through the transcellular pathway, transcellular through the cells. This will transported within the cells to the olfactory bulb, from where it will be transported to the brain. So this is the mechanism by which the drugs are transported to the brain when we are applying to the nasal mucosa. A certain percentage of drugs are also been available or transported to the blood, but that percentage is minimal, and when it is circulated in the blood, that will also transport the drug to the brain via the blood-brain barrier. So that although that would be a minimal percentage, majority will be transported through this olfactory and trigeminal nerves pathway. So when we are talking about nanoemulsion, there are different contributing factors helps in the transportation of the drug to the brain. So the first one is the droplet size. What is this droplet size? So whenever we are measuring the size of the dispersed phase, we are mentioning as droplet size. So when we are talking about nanoemulsion, means one phase will be dispersed into the other. So the dispersed phase we generally measure in terms of droplet size. So this droplet size is important because of the presence of olfactory actions. What we have said, that the drugs or the formulation will cross or penetrate from the nasal cavity to the dissolving into the cells, and of the olfactory actions in different species other than human are less than 200 nanometers. In human, it has been shown to have the diameter ranging from 100 nanometer to 700 nanometer. So that's why the size, if the size of the globules or droplets of the dispersed phase is less than 200 nanometer, it is expected that it will penetrate through the from the nasal cavity to the brain easily. So further, I already discussed that transcellular pathway for the neuronal absorption is followed when we are applying this. Another experiment has been performed by Ahmed and team, where they have come up with the conclusion that if the size of the droplets are less than 100 nanometer or around 100 nanometer, it helps in the penetration of the drugs to the brain in an effective way. So they have compared two different types of formulation. One was with average diameter of 100 nanometer. Another one was average diameter of 900 nanometer. So they have shown that the formulation with 100 nanometer, average diameter of 100 nanometer, has shown a greater extent of absorption from the site of application to the brain. So this shows the importance of droplet size when we are delivering the formulation through nanoemulsion dosage form. Further, the contributing factor is the zeta potential. We all know that zeta potential contributes to the stability of the formulation, isn't it? So if we are having the charged particles, charged globules, it helps or it repulses to each other. That prevents the coalescence of the droplets, thereby it prevents creaming formation. So it has been hypothesized that if the charge is greater than plus 30 millivolt or less than minus 30 millivolt, it produces the repulsive force in such a way that it stabilizes the formulations. Then the question arises how this zeta potential helps or contributes in the transportation of the drug to the brain. So if you see the figure provided here, this figure has been adapted from Young et al. 2012. They have mentioned that this mucin, the mucous area, it contains the mucin. Mucin contains the negatively charged ions. So you can see it from the figure. So if we are having the positively charged globules or droplets in our formulation, it will cause binding of the formulation to the negatively charged ions. So it will cause an electrostatic force by which it will allow the longer retention of the formulation to the site of application. Thereby, it will help in the penetration of the drug to the brain. However, in the literature, if we see most of the nanoemulsions which are from the literature, it has been reported that the zeta potential of the published article or the nanoemulsions are negative. So that's why we have to bring into consideration this positive zeta potential of the nanoemulsions in order to get benefits when we are targeting to the brain. Next, we'll move to the strategies which could be adopted in order to improve the intranasal deliveries. So whenever we are applying any solution to the intranasal cavity, intranasal area, what will happen if we stand up? Because of the gravity or fluidity of the solution, it will come out through the nostrils, or it can go to the other side. So it will not retain within the site of application. Thereby, it can prevent or it can hinder the absorption or transportation of the drug to the brain. So studies have shown that if we increase the mucoadhesivity of the formulation, it will allow the formulation to return to the site of application for a longer period of time. Thereby, it will facilitate the transportation of the drug to the brain. So this increase in retention could be facilitated by the addition of mucoadhesive polymers within this, or by conversion of this nanoemulsion to the nanoemulgel, or by converting this nanoemulsion to in situ nanoemulgel by incorporating some stimuli response mucoadhesive materials. Whatever we will be incorporating into the formulation will allow the binding of the formulation to the mucus. So the interfacial forces of the region of application will increase. Thereby, the retention of the formulation to that area will increase. That will facilitate transportation of the drug. So to elaborate, let's say this is the formulation. We are having mucoadhesive polymer with it. So if it is containing a mucoadhesive polymer with the formulation, which will allow binding of this formulation to the mucin chains. So if it binds to the mucin chains, it will allow the formulation to retain over there for a longer period of time, which will facilitate the transportation of the drug. So I just wanted to bring our own findings, which has been published recently on in peer-reviewed journals, where we have developed the rotigotine nanoemulsion. So rotigotine nanoemulsion was developed by using spontaneous method, by using low energy emulsification method. So in order to improve the mucoadhesivity of the formulation, we have incorporated chitosan, medium molecular weight chitosan within the formulation at a percentage of 1%. We have the results have shown that the viscosity of the formulation was increased significantly. At the same time, the mucoadhesive force was also increased. In order to determine the mucoadhesive force, we have collected the mucous membrane from the goat, from the slaughterhouse. So it was kept in normal saline first. Later, it was fixed to the instrument, applied the formulation to the mucous membrane first, and the probe was attached to that formulation applied mucous membrane. After a certain period, the probe was detached from the surface and the force was measured, which we need to detach the probe from the mucous membrane. So that was expressed in terms of Newton here. So you can see the force has been increased significantly when we have incorporated mucoadhesive polymer within the formulation. Similarly, another research where we have tested the presence of different chitosan at different concentration. We have used the low molecular weight chitosan, we have used medium molecular weight chitosan, we have used high molecular chitosan at different concentration, 0.5 and 1%. From the representation, it could be clearly understood that the mucoadhesive force is increasing with the increasing in concentration of the polymer within the formulation. At the same time, with the increase in molecular weight also having a similar type of effect, increasing in molecular weight, also increase in the mucoadhesive force. For tell me searcher to target nose to brain. So the second approach is the formation of nanoemulsion from the nanoemulsion. So whenever we are delivering any drug through this nasal mucosa to the brain, we are always preparing oil in water type of emulsion. So oil will be dispersed into the continuous phase of water. So if the water is the continuous phase, it would be quite easy for us to convert this nanoemulsion to the nanoemulsion gel by incorporating a suitable polymer within it, let's say carbopol. So if we incorporate the polymer, it will increase the viscosity of the formulation when we will measure by using any viscometer. At the same time, it will increase the mucoadhesion of the formulation. In a study by Ahmed et al., they have shown that if we increase the viscosity by means of incorporating some polymer within the formulation, within the nanoemulsion, it has shown there is an increased retention of the formulation to the application site. At the same time, it increases the permeability of the drug to the brain. So in this context, I wanted to bring one more research conducted by us, where we have developed the nanoemulsion of naringenin. So in this, we have used the oleic acid as oil phase. Not only oleic acid, we have incorporated Cepsol 218 also in the oil phase. So in order to increase the mucoadhesive force of the formulation, we have incorporated two carbopol varieties. So carbopol 934 and carbopol 940. So we have done a comparative study and we have seen that the increase in viscosity as well as increase in mucoadhesive force of the respective percentage of this nanoemulsions are almost comparable. So we have increased or we have introduced the carbopoles at a percentage of 1%, 1.5%, and 2%. So we can see the increase in percentage of carbopole increases the mucoadhesive force of the formulation. The last approach would be the in situ nanoemulsion formation of the nanoemulsion. In situ, we will incorporate some stimuli responsive polymers within it. When we will apply to the site of application, let's say the intranasal cavity, it will convert the solution to gel. So we will get the advantage of this liquid formulation, because when we'll keep this at room temperature, we'll find the advantage of liquid characteristics. So when we will apply to the site of application, it will become gel. So this stimuli could be thermoresponsive. That means when we will keep this nanoemulsion with the polymer below 30 degrees centigrade at room temperature, it will be acting as a liquid. But when we will apply to the nasal cavity at the temperature of 33 degree to 34 degree, it will become jellified because of the thermoresponsive nature of the polymer incorporated. It can also be pH sensitive. So the pH of the nasal cavity is acidic. So at that acidic pH, then it could facilitate the gel formation at the site of application when it will be applied. So this conversion of the solution to the gel following intranasal administration will help or better dosing uniformity, because if we are administering the gel, we cannot measure the exact volume. But when we are administering the solution, we can easily measure the quantity to be administered. So this type of approach can give in situ formation of gel, which will release the formula drug, entrap drug at a controlled manner to the brain, to the site of application, to the brain. So in this context, just I wanted to bring up one research article by Gadave et al. So where they have developed the nanoemulgel, the in situ nanoemulgel, by incorporating poloxamar. So they have developed the nanoemulsion, a microemulsion of olanzapine, where they have incorporated two polymers, HPMC, and at a percentage of 0.3%, whereas they have used the poloxamar at higher percentage in order to convert the formulation to in situ nanoemulsion. And they have shown that when they have applied to animal models, the permission was increased. At the same time, in another way, we can increase the, or you can convert the formulation to gel form by changing the pH. In this context, I just wanted to show you one video adapted from YouTube. So we have two formulations here. Both are in liquid. How it is converting to the gel form, we will see. So after 5 minutes, it's become gel. So even after inversion, it will not be falling down. So this video has been adapted from YouTube. Now we'll move to the existing challenges which we can face when we are delivering the nanoemulsion. Increase the volume of preparation, let's say 50 ml at a single time within the lab facilities, we will find very difficult to formulate it. So we have to come up with the formula or the techniques by which these small preparations could be prepared in a larger scale within the industry. So this challenge we have to face, and we have to come up with novel techniques by means of novel instruments in order to develop the emulsion in the industrial scale. So when we are preparing in the laboratory scale, either we are using the simple agitation by using vortex mixer, or we can use the sonicators, or largely we can use the high-speed homogenizers in order to prepare the formulation. So similar concept or similar industrial instrument should be available whenever we are planning for scale up of this formulation for large scale preparation. Next challenge will include the toxicity of these formulations. When we are preparing any nano emulsion for intending to nose to brain delivery, we generally perform the nasociliotoxicity. Nasociliotoxicity is done ex vivo by using the nasal mucus. So we are just collecting the nasal mucus from the animals, and we apply the formulation. We keep it for 2 hours to 24 hours. Then we clean the nasal mucus by using normal saline, and we go for histopathological studies. This is a very short span of study. But when we are targeting Alzheimer's disease or Parkinson's disease, we could not administer the therapeutics within a 1 day. We have to continue the treatment for a longer period of time. So in that case, we have to provide long-term therapy. So in that case, whatever the formulation ingredients we are incorporating may harm the nasal epithelium or nasal mucosa. So if there is a damage to the nasal mucosa, this can lead to bleeding or irritation to the site of application. So we have to establish the method by which we can establish the safety of the formulation when we are preparing any formulation for nose to brain delivery. So this long-term toxicity studies are essential when we are planning such preparations. The third challenge includes the approved excipients. Whenever we are preparing any formulation targeting to brain, we generally use generally regarded as safe excipients, GRAS, GRAS excipients. But if we see the list of excipients available in US FDA inactive ingredients intended for intranasal delivery, we will find a very few numbers of excipients. This is approved list of chemicals for the different routes of administration. If we download this list, we will find the list of chemicals for nasal applications as well. So in this list, we will find very few chemicals which are approved for nasal applications, which includes the oleyl polyethylene glycol, polyethylene glycol 8-stearate, polyethylene glycol 3350, polyethylene glycol 400, polyethylene glycol 6000, polysorbate 20, polysorbate 80, propylene glycol, and sorbitan trioleate. So the list is very small. The choice of excipients is very limited. So we have to formulate our formulations by using these ingredients whenever we are planning for a long-term goal. So if we wanted to commercialize or if we wanted to patent the formulations, so we have to choose the excipients which are there in the list provided by US Food and US FDA, Food and Drug Administration. Okay. So the next challenge is the associated physiological disorders. Whenever we are applying any formulation to the nasal cavity, if we are having any physiological disorder, let's say if we are having runny nose, what will happen? It will drain the applied therapeutics from the site of application. If we are having allergic reactions, let's say we are having a sneezing problem, then it will also expel out the formulation from the nasal cavity applied area. Therefore, future research on intranasal nanoemulsion should take a different degree of nasal mucociliary clearance into consideration and study the effect in a suitable animal models would be necessary. So this is another challenge. Next is the drug distribution studies in human brain. We are analyzing the distribution of the drug in animal models, in animal brain, by dissecting the brain, by analyzing the drug concentration in the brain. So this could not be possible when we are analyzing, if we wanted to see the drug distribution in the human brain, isn't it? So this is the major challenge, though we have to come up with specialized models by which we can predict that the transportation of the drug would be efficient when we will be applying through the nasal cavity in terms of animal models or in terms of in vitro saline models. So those need to be established in near future. So these are the different challenges which we generally face when we are targeting the therapeutics through this intranasal route to the brain. So from this discussion, we can come into the concluding remark that these nanoemulsions are an efficient platform to deliver the therapeutics from the nasal cavity to the brain directly, bypassing the rigid barrier of the blood-brain barrier. However, success of this delivery system depends on future research and should be directed towards safety and toxicity evaluation for long-term use. So different intranasal nanoemulsions for migration, Alzheimer's disease or Parkinson's disease have been filed for patents. This shown the interest of the route, but still we are in research stage for the nanoemulsion approach when we are targeting to brain disorders. So these are the different references which I have adopted in order to prepare the slides. And finally, I would like to thank you all for your patience on listening my lecture. Thank you so much. Now the session is open for question and answer.
Thank you so much, Dr. Bapi. This is really a wonderful session, and in between you have added some virtual videos, and so we clarify whatever the doubts we have.
Right.
Am I audible?
This game as well.
Okay, so you start your quiz series, then after I can conclude.
Okay, thank you so much. So let me share my screen again. Second. So is my screen visible to you? Is my screen visible to you? Which has been shown at the top of the screen, www.kahoot.it. Followed by, it will ask the game pin and your name. So you can put your nickname to participate into this quiz. Very good. I found one of the participant already joined. So I request you all to participate in this session. The questions prepared in this quiz are solely based on the lecture which we have discussed just now. Usually 1 minute I set because of this virtual platform. Usually this I include after my each lecture. So in that case, I keep 30 seconds or even 20 seconds. But because of this virtual platform, I have increased the time for each question.
That will be fine. No issue.
So Professor Priti, shall we proceed?
Hello.
Yes.
So we are declaring the results. Or we are waiting. $18 players has participated.
Yeah, so far. So we can start it now because the pin will be available on the screen. So the participants can join even later if they wish to. Shall we start, Professor Piti?
Yes, you can.
Okay, thank you so much. So I prepared 8 questions based on the lecture. The first one, which of the following pathways help transportation of drug to the brain after intranasal administration? So we have seen different pathways during our lecture session. So you please choose the correct answer. Transportation of drug through the conventional drug delivery, conventional oral route or parenteral route. So whenever we are administering the drugs, so would it be true or false? 2 more answers. Anybody would like to join? Even now, the game pin is available on the screen.
I request all the participants to kindly join this series. It's very interesting one. The thing is, you have to log in by www.kahoot.in, and you have to enter that pin over there.
Exactly. So 100% correct answer. Congratulations.
Oh, that's who is
Very
this?
good. So there's no change in the scoreboard because Prakar was leading, followed by Radhika and Ravikaran. So the scoreboard is showing the same. We'll move to the third question. Let's see what happens later. This is another true false question. So negatively charged droplets of nanoemulsions are better attached to the positively charged mucin. This is true or false? Please concentrate on the statement which is provided. Negatively charged droplets of the nanoemulsion and positively charged mucin.
Those who don't know how to play the game, please write the answer on a chat box. Negatively charged droplet of nanoemulsion are better attached to the positively charged mucin. Is it true or false?
So to participate in this, you can simply type kahoot.it and you need to use this game pin. Oh, very little right answer because of the confusion. What I have informed me in my lecture that positively charged droplets of the nanoemulsions are bound to the negatively charged mucin. We have shown that presence of carboxyl ion, it creates the negatively charged mucin surface. So this is not positively charged mucin. The statement was wrong. So the answer would be false. So congratulations to the winners. Let's see. Oh, there's a change in the scoreboard. So Prakhar has moved to the fourth position now. Ravikiran is leading, followed by Kusuma and Netra. So next we'll move to the fourth question. This gap fill up. So average diameter of olfactory axons in humans. I have asked in human, not in other species. Please choose the correct answer. What would be the diameter of olfactory axons? Still, there was answer in all categories, but I found 5 correct answers among them. So the size, the diameter, average diameter of the olfactory axons in humans, it is 100 to 700 nanometer, not in micrometer range. So at the same time, if it is less than 200 nanometer, it's generally found in other species. So that's why the size of the droplets when we are delivering or preparing any formulation to target brain is important. So moving to the scoreboard, we can find there's no change. Ravikiran is still leading, followed by Kusuma and Netra. We will move to the next question. This is the fifth question. This is also true false question. Mucoadhesive excipients in the formulation allow bioadhesion and enhanced retention of the formulation to the area of application. Is this true or false? So very fast answers are typed by the candidates. Very good.
Participants are very
So
attentive in your session. They know the test series is going to be available, so they are very attentive. So they are just within a second, 17 answers you will receive.
exactly, majority of the answers are correct. Thank you for your correct answers. So let's move to the scoreboard. So still there's no change. Ravikiran is leading,
Again,
followed by Kusuma and Netra. So moving to the next question. Sixth question. It's a quiz. Which of the stimuli sensitive polymers can be used to develop stimuli in situ nanoemulsion gel? So you may find multiple answers in this, but you need to choose only one. So, so So there might be multiple correct answers. You have to choose any one of the correct answer. Exactly. It should be thermoresponsive as well as it could be pH responsive. So 10 out of the 17 answers are correct. Very good. So moving to the scoreboard, there's no change in the scoreboard. Ravikiran is leading. So
congratulations.
congratulations, yeah. So moving to the next question, seventh question. This is a true false question. Global size of nanoemulsion affects the retention and permeation of the therapeutics to brain through nasal mucosa. Is this true or false? Exactly, this is true statement. So congratulations to the winners. I found that 16 answers are correct. Very good.
The improvement now.
Yeah, exactly. So let's see the scoreboard.
Oh my
So
God.
this,
Ravi Kiran again.
yeah, no change in the scoreboard. So Ravikiran is leading, followed by Kusuma and Netra. So let's see the last question, if it changes the scoreboard or not. This is also a quiz. Which of the following challenges are associated with nose to brain delivery? Might be multiple answers. So you have to choose any one. All the components as challenges when you are delivering or planning to deliver this nanoemulsion through this international route. So congratulations to the participants. Now we will see the overall result. So the third position goes to Netra. Second position is occupied by Kusuma. And the first position, most probably Ravikiran. Yes. Congratulations to the winners.
And
So I'm stopping sharing of my screen here.
once again, thank you, Dr. Bapi. This is a wonderful and knowledgeable session we have attended today. And really, I'm getting personal messages by the participants that it's too much informative, and whatever the questions we want, we want to cover in between, I think I supposed to ask, but you have covered each and every questions in your quiz, and after the correct answer, you have given the reason and correct answer, explanation for the correct answer. So it's really a wonderful session.
Oh, thank you so much.
So have you worked on the patent also for the your work?
Not yet, because I have started my research work recently. As you have explained that earlier, I was mostly engaged in administrative duties because I was associated as with the Lincoln University College as deputy dean. So just I moved to continue my research. Presently, I am working in TLS University. So maybe in near future, I'll just move to patent any of the formulation, but
Definitely,
still
if you
time
have
is there.
completed your rest of the parts, it will be comes under the patent filing work. And moving to the next question, what I have in my mind, what other formulation we can prepare for nasal drug delivery other than this nanogel?
As I mentioned in my slide earlier, so even nanoparticles could be delivered by this pathway. So we are having the chitosan nanoparticles. We are also having polymeric nanoparticles. We are having the solid lipid nanoparticles. Even micellis could also be approached. So there are several approaches. Even some of the researches included only hydrogels. So they have solubilized the drug in an aqueous media, where they have prepared the gel by using some polymer into it. So they apply it to the nasal area and utilize this route only, not the formulation. So route to deliver the drug from the nasal cavity to the brain.
Okay. Uh, one more question I just wanted to know. What
Mhm.
about the polymer fate in the brain targeting, brain drug delivery when we are giving?
Polymer-free dendrimers.
Yeah, that will be the fate of polymers in the drug brain drug delivery.
Could be done. So, so dendrimers are also engaging in delivering the drugs to the brain via nose to brain, nose to brain route. So there are several researches are evidenced in the literature as well. It's also could be done.
Okay, thank you so much. And lastly, I just wanted to know that you are in the PRISAL platform, the Pharmaceutical Royal International Society. What message you wants to give to our participants?
Uh, I couldn't get you actually. There was a voice cut when you just delivered it.
I said, what message you want to give to all the participants?
Oh, so if the participants are from the pharmacy background, I would suggest to do the research in such a way that it should bring a novel formulation in the future, so that we can commercialize it in the benefit of the public. So that is the message which I wanted to pass to the researchers. So that's all.
Thank you once again.
Thank you.
Now moving towards the concluding ceremony, uh, I'm sharing my slide. The Pharmaceutical Royal International Society take a privilege uh, to welcome our Dr. Bapi Goran as a research associate. Thanks, Dr. Bapi Goran, for delivering such a knowledgeable session on nose to brain targeting of nanoparticles, a boon to targeted CNS disorder, which is really one of the new perspective, as we all knows that intranasal route of administration is one of the best route to deliver the drug to the brain, and the drug is also required in a lesser amount, and it will help to target the various CNS disorders like Alzheimer, meningitis, Parkinson's, and migraine. And even with this this advanced training program, we can plan the various modules, and hopefully we can somehow fulfill the criteria. As I really admired your session, as you have give your precious time, because without any training we lacked knowledge, and without the knowledge we lack the confidence, and for the confidence we definitely require to train ourselves. So without confidence we are lacking of victory. So this is the mission of our advanced training program, and I heartily thanks once again for joining PRISAL platform and sharing your knowledgeable session. Thanks once again from the bottom of my heart.